we've been doing a lot of different things with moles, and the next thing we're going to do with moles is a concept called molarity. And the short part of this is that molarity is just a unit of concentration, but it's going to combine a lot of the different tasks that we've been doing previously in this chapter into one particular problem. So if you don't understand how to convert grams to moles and how to find molar mass, then this is going to be a challenge to you. So you got to make sure you have a good, strong background before you even start this particular section. Okay, this first page, just kind of a little review. By now you should know that a mole is an amount of something, and that it is 6.022 times 10 to the 23rd. And you should be aware that we can be talking about molecules or formula units. In fact, I have this particular page I just want to go through. A formula unit is something that refers to substances that have what type of bond? And at this point in time, you better be saying ionic. And when you say ionic, you better be realizing that an ionic bond was when I had an attraction of different charges. Okay? So I had a positive and a negative charge, and those things were attracted to each other. Okay? And then molecular mass refers to things that are covalently bonded. And that's when we had a sharing and we were drawing different dot structures of different things, like H2O, and those electrons in there are sharing. Okay? Now, the bottom line here, though, is when we're making a calculation using Avogadro's number or molar mass, okay, it does not matter what we call this, okay? It makes absolutely no difference whether you call it a formula unit or molecular mass. In fact, I made a couple calculations here quick where I have molecules of H2O and I have formula units of NaCl, because this is a covalent bond and this is an ionic bond. But again, if I make the calculation, this number right here, Avogadro's number, is the same in both cases, and the number of moles comes out to be the same in both cases. So, bottom line is, you got to know that there's a thing called formula units and molecules. They mean the exact same thing. Now, we're going to get into this whole idea of concentration. Concentration is how we measure how much of a substance there is mixed with another substance. Okay? And when we talk about substances that are concentrated, that means what to you? And hopefully you're saying that, well, if something's concentrated, there is a large number of particles dissolved that are present in the solution. Okay? And so these particles that we're talking about here are ones that are dissolved, and there's a lot of them. Okay? And another word that goes along with this is the word dilute. And when we talk about dilute solution, we mean that there are a small number of particles that are dissolved in the solution. Okay? And you always think about, or you can think about, concentrated orange juice when you think about this. If you buy frozen orange juice from the store and it's concentrated, it comes in a can, okay, and there's a large number of particles present. But then what you do is you take that and you add water to it and then you dilute it. Okay? Now, just to give you an idea here, okay, here is a solution of copper sulfate. And in the solution of copper sulfate over here, okay, it's very dilute. And in this second picture here, we're adding more of the copper sulfate, so we're making it more concentrated. And you can see that it's more concentrated, in this case, by the darker appearance. And then we add even more copper sulfate, and we get an even more concentrated solution. So over here, we're dilute. And over here, we are concentrated. Okay? And we just have a whole lot more particles in the solution on the right side than we do over here in the solution on the left. And again, here's another picture that I pulled off the internet. Okay, down here we have very few particles in the solution, so it's dilute and it's kind of a pinkish color, where as we go across here, we keep adding more and more of this red particular color until we get to this end, and we're very concentrated down here. Down here we have a lot of particles in the solution. Here we have very few particles in the solution. Now, when chemists measure this then, the way chemists measure concentration is they measure how many particles there are in the solution. And this measurement, okay, can look a number of different ways. Okay, so here I have a little thought experiment that I would like you to do. Okay, I have 4 samples of beakers, A, B, C, D, and they all have the same amount of water. Okay, but in beakers A and B, I'm going to put 5 grams of sugar and 5 grams of salt. Okay, this sugar is normal table sugar, C12H22O11, and the salt is normal table salt, NaCl. Okay, and then in beakers C and D, we're going to put 10 grams and 10 grams. Okay, so that's what I have here. Here's my 5 grams of sugar, 5 grams of salt, 10 grams of sugar, 10 grams of salt. Now, when I put those in there, the first question I'm going to ask you is, which one do you think is the strongest? And you might have a hard time picking this out. You might be saying, okay, well, C and D both had 10 grams in the same volume of water, because everything is the same volume of water. So because there's 10 grams here, you might think, well, it's hard to choose. Those two should be the strongest. These two each had 5 grams. Those two should be the weakest. Okay? So then that was kind of my next question. Which do you believe is the weakest? Well, these two should be weakest, but how do I tell which one is the weakest? Well, we need to look at this in a different way. Okay? And what we need to look at is, we need to look at this in terms of moles. And what you got to remember is moles essentially equals number of particles. So what I want you to do is I want you to calculate the number of moles that are present in each of the above solutions. Okay? So right now you're going to stop and you're going to calculate the number of moles that are present in each of the above solutions. Okay, so if you made those calculations, these should be the calculations that you have. For the 5 grams of sugar, you should have calculated you have 0.015 moles. For the 5 grams of NaCl, you should have 0.085 moles. And then for the 10 grams of sugar, you should have this. And for the 10 grams of NaCl, you should have that. Those would be the calculations that you should have made. Now, so if I go back up here, this 5 grams of sugar, I have 0.014 moles, which means I have a certain amount. And if I compare that to the 5 grams of NaCl, one of the things I see is I have a greater number of moles of NaCl than I do of sugar. So even though I had the same mass, this was 5 grams and this was 5 grams, I have more moles here. So this solution here is more concentrated than this one. So I can eliminate this one as being one of the most concentrated. So then I would think, well, if I put in 10 grams of sugar, that 10 grams of sugar would certainly be more than 5 grams of NaCl. But what you realize is it's actually not. Okay? 0.085 moles of NaCl is much bigger than 0.029 moles of sugar. So in fact, we go all the way to sample D, and we say that in sample D we have 0.17 moles of NaCl. So in terms of moles, sample D actually has the most particles in the 50 milliliters of water. So sample D is actually the most concentrated, and probably by surprise, sample B is the second most concentrated. Then it's sample C, and then it's sample A. So that's probably a surprising fact to you. But the bottom line here is we cannot determine concentration by looking at mass. Okay? What we have to do is we actually have to look at moles that are in the solution, because the moles are actually our number of particles. Now, how do chemists do that? Well, chemists use a unit called molarity. Molarity is the chemist's concentration unit. And what molarity is, it's the number of moles that you have per liter of solution. Okay? And let me repeat that. It's how many moles you have for every liter of solution that you have. So there's an equation that comes along with this. And that equation we call the molarity equation. And that equation just simply says it's the number of moles divided by the number of liters. Okay? That's your molarity equation. Now, I always shorten this down to capital M, which stands for molarity, is moles divided by liters. Okay? This makes the most sense to me, and it's just a lot easier than writing everything out. Okay? Now, with this, one of the things we have to look at is the unit of molarity. Okay? And if I take a mole divided by a liter, my unit is moles per liter. Okay? But what chemists do is they change that unit to a capital M. And that is said molar. Okay? So the way that would be, it would be something like this. I could have a 0.5 M NaCl solution. Okay? And now, what does that mean exactly? Well, what that means is I have 0.5 moles for every liter. And actually, going back to this, the way I would read this is a 0.5 molar NaCl solution. So I have 0.5 moles for every liter. Okay? If I had a 0.01 molar HCl solution, that would mean I have 0.01 moles for every liter. Okay? Now, remember, moles can be translated into particles, because I can take moles and I can change them into particles by multiplying by Avogadro's number. Okay? So instead of dealing with Avogadro's number and the times 10 to the 23rd or times 10 to the 24th of something, we just deal with moles. Okay? Because that makes our life easier. If I want to compare a 3.0 molar NaCl solution to a 1.5 molar NaCl solution, which one has more particles per liter? And the one that has more particles per liter is the one that's 3 molar. So this one is more concentrated. And it's more concentrated because there's more particles for every liter of solution. Okay, so molarity is the way that we calculate concentration. Okay, now, there's a lot that actually goes into these particular problems. One of the things that goes into these problems is we're going to make an assumption. And the assumption that we're going to make is that you remember that 1 liter is 1,000 milliliters and 1 liter is 1,000 cubic centimeters. And the reason why we need to remember this is because most of my problems give you volumes in milliliters or liters, and we have to change them. So in all of your problems, you're probably going to have to change milliliters or cubic centimeters to liters. And that's something that I actually expect that you can do in your head, and you never have to show me. Okay? But I'm going to show you one right here. So if I have 250 milliliters and I want to change that to liters, I would take 250 milliliters and I would make the conversion, and I'd put 1 liter all over 1,000 milliliters. And hopefully you would not have to do that in your head. 250 divided by 1,000 is 0.250 liters. Okay, quite honestly, this is a conversion you should be able to do in your head, and you should never, ever, ever have to show me this. Okay, so let's look at a problem. And there's a lot that goes on to these problems. So take a moment to write down this problem in your notes. Okay, if you don't have this problem written in your notes, you will have to go back and re-watch this vodcast or go back and fast forward to it, because I will not accept it unless this is in your notes as an example. Now, there's a lot going on in this particular problem. The first thing that's going on in this particular problem is I want to know what is the molarity. So, I write down my molarity equation. Molarity is moles divided by liters. Okay, so then I realize, well, I don't have moles. Okay, what I have is grams of potassium chloride. So again, by now you better be getting good at writing formulas. Okay, if not, okay, you're going to have to go and write this formula correctly. But I have 85 grams of KCl. I do not have moles, but you've done a worksheet now that allows you to convert grams to moles. So I need to go ahead and make a side calculation where, first of all, I need to convert the 85 grams into moles. So I'm going to set up a little T box, and you will show me this calculation, okay, where I have to convert this 85 grams to moles. So I'm going to multiply this by the molar mass of KCl. Now, here's something that I no longer want you to show me. Okay, up to this point, you have to calculate the molar mass of KCl. So off to the side here, you should be going to the periodic table and you say, okay, potassium is 39 grams per mole and chlorine is 35.4 grams per mole. So I'm going to add those two up and I'm going to get 74.4 grams per mole. That's the total molar mass of that compound. Okay, and so this right here, I never want to see that calculation. What you should do is you should be taking out your calculator and you should type in 39 plus 35.4 and be done with it, and then just write down what the molar mass is in your problem. So 74.4 moles is what you write here. I do not want to see this anymore. You shouldn't have to show me. You should just be able to type it into your calculator. Okay, so we do this math and we find out that we have 1.14 moles of KCl. So I now have my number of moles. Okay, I go back to my problem. Okay, I say, okay, I have 400 milliliters. Okay, 400 milliliters. So my volume is 400 milliliters. I need to convert that to liters. Again, this is something that you should be able to do in your head. So this is 0.400 liters. Now again, I don't really want to see this, but the way I did this was I took 400 milliliters times 1 liter divided by 1,000 milliliters. That's how I got that. You should not have to show me that. You should be able to just do this in your head. So I want to calculate the molarity. Okay, so the molarity is my moles, 1.14 moles, divided by my liters, which is 0.400 liters. So my molarity is going to be 2.85. And now, remember, moles per liter is a capital M, molar. And then this is KCl. So this is how we would write the answer to this question. And how you would read this is a 2.85 molar KCl solution. It's 2.85 molar KCl. And that means I have 2.85 moles for every liter of solution. It's an amount, okay? So again, this is a concentration. Let's look at another problem. Let's determine the molarity of a solution that has 6.75 grams of ammonium iodide. And I have 130 cubic centimeters of the solution. Okay, so the liters is easy to get. Okay, we have this, let's just pull that out. I have 0.130 liters. You should be able to get that, no problem. Okay, but if I'm going to get the molarity, again, molarity is moles per liter, what do I have to do to this term? Okay, hopefully you're saying, well, I have to take that 6.75 grams of NH4I, and I have to change that to moles. And how do you do that? Multiply by molar mass. Again, we did lots of worksheets with this. So I'm going to take 6.75 grams of NH4I, and I'm going to set up a T box, and I'm going to multiply it by the molar mass of NH4I. So now, what am I doing? Okay. In my calculator right now, what I'm doing is I'm looking up nitrogen, okay, and I'm typing 14 because that's the molar mass of nitrogen. I look up hydrogen, which I know is 1. I have 4 of those, so I'm going to add 4. So I have 14 plus 4 in my calculator. Then I just look up iodine, and iodine is 126, I believe. Yep, iodine is 126.9. So I just looked that up. And I just add all those up in my calculator, and I get 144.9 grams. Never once did I write this on my paper, because I don't need to anymore. And I do this math, and when I do this math, I get 0.04 moles of NH4I. Actually, it's 0.046. And now I want to calculate my molarity. So my molarity is 0.046 moles divided by my volume, which was 0.130 liters. So my molarity is 0.35. And what do I write for a unit? Molar NH4I. Okay, and that is my concentration. Okay, so that's how we determine the molarity of a solution. You find your number of moles, take your moles, divide by your liters. Now, we're going to switch this up a little bit, and what we're going to do now is change this to figure out how could I determine the mass of a substance that I would need to actually make a molar solution. Okay? I need to see this problem in your notes. So make sure you go ahead and write this one down. And again, I didn't give you the formula of any of these, okay, because you should be good at coming up with formulas on your own. So the formula of silver phosphate you should be able to write out directly by now. Okay, so here's my problem. I want to know how many grams of silver phosphate are needed to make 500 milliliters of a 6.5 molar solution. Okay, so what you're looking for is grams. Okay, now what you should say to yourself is, well, I have a molar solution, or an equation for molarity, that says I need to take moles divided by liters. So how the heck am I going to find grams from this? Well, the way you're going to find grams from this is you're going to have to think in terms of, can I get grams from moles? And so one of the things that we know is if I take moles and I multiply that by the molar mass of something, that gives me grams. So what I'm really looking for is I'm really going to take this equation and I want to solve it for moles. Okay, that's what I want to do. So as a little sidebar down here, okay, I'm going to take this equation. I have molarity equals moles per liter. To solve this for moles, I'm going to multiply both sides by liters. That would cancel that out. So in order to calculate, in order to calculate moles, moles would be molarity times liters. I don't know why I canceled that out because I just put it over there. Okay, well I have the molarity. The molarity was given in my problem. The molarity was, it's 6.5 molar. Well, my volume in liters is right there. And that's 0.500 liters. So, if I want to find out what my moles are, I'm just going to take my 6.5 molar, which is really moles per liter, times 0.5 liters. That cancels out that, and that tells me that my number of moles is 3.25 moles of Ag3PO4. Now, am I done? No, because what I want is grams. So I want to change this into grams. Well, that's what we were doing 2 worksheets ago. We were taking moles and changing them into grams. So I just need to find out how to do that, or not find out, remember. And the way to do that is I take 3.25 moles of Ag3PO4 and I multiply it by the molar mass, where I put the number of grams of Ag3PO4 up here, all over 1 mole. And so now, what are you doing? Well, you're going to take out your calculator and you're going to find your periodic table and you're going to look up Ag. And you're going to see that Ag is 107.9 grams per mole. So you're going to take 107.9 times 3 in your calculator. Okay, and then you're going to find phosphorus is 30.9 grams per mole. So you're going to add that to this. And then you're going to find oxygen is 16 grams per mole, and you have 4 of them. So you're going to add that to that. So you're going to add all those up in your calculator. You're not going to show me this unless you really have to. Okay, if it's more comfortable that you show me this work, okay, then go ahead and do it, but you no longer have to. I want you just doing that in your calculator, and then in your writing in here, well, that's 418.6 grams. Now, when I multiply this across, okay, the moles cancel, and you're going to get a big number here. You get 1,360.45 grams of Ag3PO4. And then you really need to stop and think, what the heck does that mean? Well, what this means is if I have 1,060 grams and I put that into 500 milliliters of water, I am going to get a 6.5 molar solution. Okay? Now, what I want to show you is how you can do this all in a tea box. Okay? Instead of doing this step by step by step like we did here, you could actually do this all in kind of one long tea box. Because to get moles, remember, what I did was I took molarity times the liters, and then I actually took that times molar mass. Well, what if you put all that into a tea box, where I started with my 6.5 molar solution, which was 6.5 moles per liter, and I multiply that by 0.5 liters. Okay, if I stop there, okay, I'm done, I have my moles, but I don't want to stop there. If I take that and I put in 418.6 grams of Ag3PO4 per 1 mole, now my moles cancel. And if I do all that math, okay, I'm going to get the same mass that I got up there, 1,360 grams of Ag3PO4, and I did it all in a tea box. So the tea box is kind of helpful. So either way is beneficial. Now, what some people don't like is there is nothing that you put in that spot, and that's actually okay. There doesn't need to be anything there. We're going to do this problem using this tea box method only. So go ahead and write this down. And again, what I'm looking for is how many grams. Okay, and I have a 2.00 molar solution, and I have 0.150 liters of it. And again, I'm making this calculation of 150 milliliters times 1 liter all over 1,000 milliliters. I'm just doing that in my head. I never really want to see that. Okay? I don't want to see it. It should not be there. You should be able to do that in your head. Okay? So the only thing that you're going to have to do as a side calculation is you're going to have to come up with the molar mass of cobalt chloride. Okay? And again, that's something you can do on your calculator. So let's start with our tea box. Okay? Again, I want to calculate moles, so I'm going to multiply molarity times volume. So I'm going to take this 2.00 moles per liter. Okay? Remember, this is moles per liter. That's how I got that. Okay? I'm going to multiply that by 0.150 liters. That cancels out my moles. And then what I'm going to do is I'm going to multiply that by the molar mass of cobalt chloride. And again, you're taking out your calculator, you're typing in the mass of cobalt, and then the mass of 2 chlorines, and all you're writing down is 129.7 grams right here. That's all you're doing. Run through the math, and what you get is 38.9 grams of cobalt chloride. And remember, what exactly does this mean? Well, what this means is if I take 38.9 grams and I put that into 150 milliliters of water, I am going to get a 2 molar solution. You should now have enough information to work on your molarity worksheet.